Hi everyone. Today, let's learn about a special type of complex root of a polynomial, which is the nth root of unity. Let's not learn it directly, but through a fascinating problem. Here is the problem. So, find all the complex numbers x and x power 6 should not be 1 that satisfies this equation, or the expression in the left hand side goes to 0 for that value of complex number. Let's take a closer look. 1 plus x power 22 minus x power 35 minus x power 13 is the numerator. Let's try to factorize this. We get 1 plus x power 22, and let's factor out x power 13 from the last two terms, which results in x power 22 plus 1, and that also matches with the first two terms. So we get 1 plus x power 22 times 1 minus x power 13. So including the denominator, one would get 1 plus x power 22 times 1 minus x power 13 upon 1 minus x power 6 need to be 0. So when does a number go to 0? When either one of its factor is 0. And what are the factors here? The factors are precisely 1 plus x power 22 and 1 minus x power 13. So if one of them go to 0, then the entire expression evaluates to 0. And if both of them are non-zero, clearly the expression cannot evaluate to 0. So let's impose the condition that one of them must go to 0. But there is the term 1 minus x power 36 hanging in the denominator. What should I think about that? Should I consider the values for which it is 0? And of course you have to consider, but note that x power 6 cannot be equal to 1. So x cannot take that value. So you have to avoid the roots of 1 minus x power 6. So along with this, we have the additional condition that 1 minus x power 6 is not equal to 0. And it's obvious, right? Because if 1 minus x power 6 is 0, then the denominator would go to 0, making the expression undefined. And we don't want that. So let's look into the roots of 1 plus x power 22. Clearly, it do not have any real root. Why? Because x power 22 is always greater than or equal to 0. And you have 1 added to it, which makes it greater than or equal to 1. So how can it be equal to 0? Because 0 is a number less than 1. Thus, we have only non-real roots. So let's go into the realm of complex numbers, because we are allowed to substitute complex numbers as per the question. Let x be equal to a plus ib. This representation of complex number is called algebraic form, but we are not going to use that. There is an equivalent form of this, which is known as trigonometric form of complex number, written as r times cos theta plus I sin theta. And this is just simply writing a as r cos theta and b as r sin theta. This form is known as trigonometric form of a complex number. And let's use that because we have a particular theorem that can be incorporated in this equation. So now we get 1 plus r cos theta plus I r sin theta whole power 22 equal to 0, right? So this implies r power 22 times cos theta plus I sin theta whole power 22, and this must be equal to minus 1. This is where we are going to invoke the de Moivre's theorem. If you are not aware of de Moivre's theorem, I recommend you to go back and learn it from a previous video that we did. So this theorem states the following. I will briefly tell you what this theorem states. Whole power 22 equal cos 22 theta plus I sin 22 theta. So it brings the exponent upon cos theta plus I sin theta to its angle. So this is quite interesting. So writing this, we would get r power 22 times cos 22 theta plus I sin 22 theta equals minus 1. But let's write minus 1 also in trigonometric form of complex numbers. So minus 1 can be written as 1 times cos pi plus I sin pi. Of course, sin pi is 0 and cos pi is minus 1. But this is the standard trigonometric form where 1 denotes the distance of the point -1 in the complex plane from the origin, and pi represents the angle made by the vector which points to that point -1 in the complex plane with the positive x-axis. So if you have the number -1 in the complex plane, then think about the vector that points to the point -1, 0, and this precisely make an angle of pi or 180 degrees. And this representation is known as trigonometric form that we mentioned earlier. Now we know that every number that is complex number has a unique trigonometric. That means if two complex numbers are same, then their modulus is same and their angle made with positive x-axis are also same. Thus we get r power 22 equals 1. And since we can assume that theta is in the principal range, that is theta is greater than or equal to 0 and less than 2 pi, it implies 22 theta is between 22 times 2 pi and 0. Thus, what are the values in this range that correspond to an angle of pi in the complex plane? Think about it. Suppose you have the xy plane like this, and if we consider the angles from 0 to 22 times 2 pi, we get the angle pi, which is also equal to pi, of course, and also the angle 2 pi plus pi, because once you make 360-degree rotation from pi, you will land in the same place. Thus, 2 pi plus pi would give us 3 pi. So, 22 theta can take pi or 2 pi plus pi or 4 pi plus pi, which can be generalized as 2 pi k plus pi, where k goes from 0 all the way till 21, because it cannot take the value of 22, as otherwise it would exceed 22 times 2 pi. So we now have theta to be 2 pi k by 22 plus pi upon 22, where k goes from 0 to 21. Remember that this value of k is 22 in number, and the degree of the polynomial x power 22 plus x power 22 plus 1 equal to 0. The degree of this polynomial is also 22, and it can have at most 22 roots, and we got all the 22 roots. So thus we found the roots of this polynomial. By a similar way, one can find the roots of the polynomial x power 13 minus 1 equal to 0, which is the second polynomial in our list. Now this corresponds to, I missed the value of r in the last polynomial. R power 22 equal to 1 imply r equal to 1, because r is the magnitude of the vector pointing to certain or the root here. And since it is a positive real number, it has to be 1. It cannot be negative. So thus, the values of x that satisfy this polynomial can be written as cos theta plus I sin theta, where theta is represented by this box. Alright, let's come to x power 13 minus 1 equal to 0, which is our second polynomial. By similar logic, one can consider x as r times cos theta plus I sin theta. And again, one can apply the de Moivre's theorem. One can again apply the de Moivre's theorem, and you can reach that r power 13 must be 1, and cos 13 theta plus I sin 13 theta must be 1. So, working on the range of 13 theta from 0 to 13 times 2 pi, one can get all possible values of x, which is cos theta plus I sin theta, because r is 1 now, where theta equals 2 pi k by 13, and k goes from 0 to 12. So again, we got the 13 distinct roots of this polynomial, and there cannot be more because the degree of this is 13, right? Alright, so we have solved the second polynomial also. Let's come to the third polynomial, because we have to avoid the roots of this polynomial, which is x power 6 minus 1 equal to 0. Actually, it shouldn't be equal to 0. So first let's find the values of x for which it is equal to 0. And then let's remove those roots which resemble to the roots of this polynomial. So substituting x equal to r times cos theta plus I sin theta, one will get again that r is equal to 1 and the roots are nothing but cos theta plus I sin theta, where theta is of the form 2 pi k by 6, where 0 is less than or equal to k is less than or equal to 5. That corresponds to all 6 distinct roots. So coming back to our actual expression, we have x power 22 plus 1 times 1 minus x power 13 upon 1 minus x power 6. So combining all the roots of numerator, one would get the roots as cos theta plus I sin theta, where theta is of the form 2 pi k by 22 plus pi upon 22 or 2 pi k by 13. But over here, the value of k goes from 0 to 21, whereas in the second set, the value of k goes from 0 to 12. And the union of these two sets would be the entire possible set of angles. And clearly there can be no match between these two values, because x power 13, if it is going to be 1, then we cannot have x power 22 to be minus 1, because otherwise we would get x power 8 to be minus 1, and dividing these two, one would get x power 5 to be minus 1, and dividing these two, one would get x power 3 to be 1, and again dividing these two, one would get x squared is minus 1, and dividing these two, one would get x to be minus 1. But minus 1 is not a root of x power 13 equal to 1. So this won't be true. There are no root in common. Thus this will correspond to 13 plus 22, which is 35 distinct roots. And comparing it with the roots of 1 minus x power 6, you will see that there is a root in common between 1 minus x power 6 and 1 minus x power 13, which is exactly x equal to 1. So this is 2 pi k1 by 13, which is equal to 2 pi k2 by 6. And this happens if and only if k1 equal to k2 equal to 0. Because as otherwise 6k1 won't be equal to 13k2. So we need to have both 0. And when you compare it with the first set of angles, that would be equal to 2 pi k2 by 6. So one could get some values out of this. Cancel all the 2 pi's and you will get k1 by 22 plus 1 by 44 is equal to k2 by 6. Now cancel the 2, you will get k1 by 11 plus 1 by 22 is equal to k2 by 3. So let's multiply it by 22 throughout. After multiplying by 22, you get 2k1 plus 1 is equal to 22k2 upon 3. Now that means 22k2 by 3 is an integer. So what are all the possible values of k2 for which it is an integer? We know that k2 can vary from 0 to 5. And the only multiples of 3 are k2 equal to 0 and k2. So we have already excluded the case in which k2 equal to 0, because if k2 equal to 0, actually we will not get a proper value of k1, because k1 would be equal to minus 1, and that is not allowed. Now if k2 equals 3, then one would get 2k1 plus 1 is equal to 22. And that is also not allowed, because 2k1 plus 1 is an odd number, whereas 22 is even. So there are no matching roots between these two polynomials. Thus, we need not subtract. So we have to subtract only one root, which is when k equal to 0 in the second set. So when you subtract that root, you will get that the value of k goes from 1 to 12 instead, with 35 minus 1 distinct roots, which is 34 in number. So thus, this set represents all the roots of this expression for which x power 6 is not equal to 1. I hope you enjoyed this video. The board work will be available in the description, and keep doing great mathematics. See you in the next video. Bye.